Hi, everybody. Welcome to the class on hypothesis testing. And so this one, this is the first of several classes on hypothesis testing. So today we're largely going to introduce many of the concepts and see kind of how it relates to what we saw last time. So we're going to kind of maintain our fictitious assumptions about knowing the population standard deviation. And then starting next class, we're going to start seeing what we do if we don't know any population parameters. But today's it's going to be less doing calculations, it's more just going to be kind of understanding what is involved in hypothesis testing. What does it mean? All right, so we'll start with the fundamentals of hypothesis testing, and we're going to start with an example. So a company called Procare Industries Limited once claimed that its product called Gender Choice could increase a woman's chance of giving birth to a baby girl. How could we test whether the gender choice claim is true? One way would be to study a random sample of, say, 100 babies born to women who used gender choice product. So we could see, do we see more girls in that sample of 100? If the product doesn't work, we would expect about half the babies to be girls, because normally we would expect about half of babies to be girls and half of babies to be boys. If it does work, we would expect significantly more than half of babies to be girls. The key question then is what constitutes significantly more? And this is something that we're going to return to throughout today is, how do we know, is 51 girls evidence that it seems to work? Is 52 girls evidence that gender choice works? Is 53, 54, 55? What's considered a significant difference showing evidence that it seems to work? So in statistics, we answer such questions through hypothesis testing. So consider a sample in which there are 64 girls among the 100 babies born to women who use the product. So we begin by assuming that gender choice does not work, right? So that's always our starting assumption. Let's start by assuming it doesn't work. That is, it does not increase the percentage of girls. If this is true, then we should expect about 50% girls among the population of all births to be to women use the product. So the proportion of girls is equal to 50%, right? So if it doesn't work, we should get 50% boys and 50% girls. We now use our sample with 64 girls among 100 births to test the above assumption. We conduct this test by calculating the likelihood of drawing a random sample of 100 births in which 64% or more of the babies are girls from a population in which the overall proportion of girls is only 50%. So we'll come back to this later, but you may already be seeing based on last class where this is going, right? We've got a population. We're making an assumption that we've got a population with a mean of 50% or a proportion of 50%, right? And then we've got one sample among all the possible samples with a certain value of 64. And then we want to see how likely is getting that one sample of 64 when you've got a population proportion of 50%. So we'll unpack that more, but you should be recognizing that's a lot like the questions that you had on the last quiz and the last exercises were questions that were very similar to this. If we find that a random sample of births is fairly likely to have 64% or more girls, then we do not have evidence that gender choice works, right? So if it's just, in any population, if you take samples of any size, you're going to have a lot of them that cluster near the mean, but you're going to have you're also going to have several outliers on both sides. So you're going to have some extreme values on both sides. So it could be that's, just that 64% is not unusual if you take just 100 births. And in which case, then, if it's not unusual, just for people who don't even take the product, or for women who don't even take the product, to have 64% of babies born to be being girls, then that's not really evidence that the product's doing anything. Conversely, if it's very, very unlikely from just the standard population to get 64% of babies born be girls when you have a sample of 100, then that would be strong evidence, because it's very, very unlikely that we would get that just from a random sample where the population mean is 50%. So if we find that a random sample of births is unlikely to have at least 64% girls, then we can conclude that the result in the gender choice sample is probably due something other than chance, meaning that the product may be effective, right? So in that case, we would start thinking that if it's effective, that we have a sample not of the wider population, but we've got a sample that's different. We've got a sample that's drawn from a population that has a different population mean. And one that would be, say, larger than 50, which would be suggesting then that the population parameter for those who take gender choice is different than for those of people who do not take it. But even in this case, we wouldn't have proved that the product is effective. Proof in social sciences is something that's pretty much effective. So never use that word when you're talking about social sciences. But even within the natural sciences, at this stage, we haven't proven anything, as there could still be other explanations for the result, such as that we happen to choose an unusual sample, or that we are confounding variables we did not account for. So no matter how unlikely, for example, 64% is, even if it's 1 in 1,000, it's still possible that you got that 1 in 1,000 sample. 1 in 1,000 times that should happen. So it's still possible that something else is causing it, or that it's just that gender choice doesn't work and you just got unlucky and got that really high sample. So what are hypotheses then? So a hypothesis is a claim about a population parameter, such as population proportion or population mean. So it's a claim about, say, the mean population proportion for births when you take gender choice is so-and-so, it's 64%. The hypothesis test is a standard procedure for testing a claim about a population parameter. There are always at least 2 hypotheses in any hypothesis test. In the gender choice case, the 2 hypotheses are essentially: 1, that gender choice works in raising the population proportion of girls from 50% that we would normally expect, right? So that's, hypothesis 1 here would be that gender choice works, right? It makes it, we don't know how high, but that it makes it higher than 50%, because that's what they're claiming. Hypothesis 2 is that gender choice does not work in raising the population proportion of girls, right? So it's despite what we get in our sample, the population proportion is still 50%. And so in every single, when you're setting up a hypothesis test, when you're developing your hypothesis and setting up your hypothesis test, right? Remember that every hypothesis test must have 2 hypotheses. So when we're talking about the hypothesis that gender choice does not work, we refer to that as the null hypothesis. And often we'll write it as H naught or H sub 0. So the null hypothesis is the claim that gender choice does not work, in which case the population proportion of girls born to women who use the product should be 50% or 0.5. Using P to represent the population proportion, we write this null hypothesis as H naught, P equals 0.5. So the proportion of girls born is equal to 0.5. The alternative hypothesis is the claim that gender choice does work, in which case the population proportion of girls born to women who use the product should be greater than 0.5. So we write this alternative hypothesis as H alternative, or often we'll number them, so it might be H1. The proportion is greater than 0.5. So this is a claim that they're making, that it's greater than 0.5. The null hypothesis is that this is going against the claim. So it's saying that nothing happened when from taking gender choice. So that the babies born will have the same proportion of girls as for those who didn't take it. So it's not from a different, the sample's taken from the general population, there's no separate gender choice population. So the null hypothesis will generally include the condition of equality, just as the null hypothesis for the gender choice example is that it's the equality proportion is equal to 0.5. Now that equality won't always be 0.5. It could be, different. So for example, if you're doing a drug test and normally, 1% of people die from a certain disease, right? And you're testing a drug and you want to see, does that drug reduce the mortality rate? Then you would be having a null hypothesis of, the proportion is 1 or 0.01, right? If you're testing, does, taking an exam at 8 a.m. Make, grades go up or down? If say you're studying that 8 a.m. is too early and that makes grades go, go down. So you need your null hypothesis of what do people just normally get? What is the, for people say take a QM final, what is the normal average? Say it's 75, right? So the null hypothesis is that the students will get 75%. The alternative hypothesis would be that they get, say, less than 75% because they don't do as well taking it at 8 a.m. But the null hypothesis would just be, there's no difference. Doing it at 8 a.m. has no difference. So it would be equal to 75%. However, the alternative hypothesis for gender choice case, probability greater than 0.5, is only one of 3 general forms of alternative hypothesis that we can encounter in this chapter. So almost always your null hypothesis will be of equality, so equal something. But your alternative hypothesis can take one of 3 forms. So population parameter is less than a claimed value. Population parameter is greater than a claimed value. So that's what we had here in the gender choice case, where we're saying that the population parameter is greater than 0.5. In the exam case, we're saying the population parameter is less than, say, 75%. And then if we don't know, we think that some things can happen, but we don't necessarily know the direction. We say population parameter is just not equal to the claimed value. So gender choice, in that case, we'd say, that the proportion of females born or of girls born is not equal to the claimed value of 0.5. In the social sciences, this is actually the most likely one or most commonly used one. If you have very strong assumptions about the direction, you can use one of these, but typically speaking, most hypothesis testing is using the not equal to 1. So it's useful to give names to these 3 different types of alternative hypothesis. And so the one where we said less than is it's called a left-tailed hypothesis test because it requires testing whether the population parameter lies to left or lower value of a claimed value. So again, if you think of a normal distribution, right? If you're saying that something's less than, you're looking that way to the left, and you're looking into the tail, right? Because remember how it tapers off. You get observations of further out, become less and less likely. So you kind of move into different tails. So if we're talking about less than, we're looking at the left tail, so the lower than tail. Greater than, we're looking at the right tail because it requires testing whether the population parameter lies to the right. It was higher than, greater than. So greater than 0.5, say. And then not equal to is called a two-tailed hypothesis test because it requires testing whether the population parameter lies significantly far to either side of the claimed value. So we're not making a guess about whether it's the right or left side. We're just saying it's far. It may be far that way. It may be far that way from the null hypothesis, from the claimed value, but we don't know necessarily which direction. So if we talk left-tailed, we're saying less than. If we're talking right-tailed, we mean more than. If we're saying two-tailed, we just mean far, but not necessarily any particular direction. So the null hypothesis, H naught, is a starting assumption. So kind of just to summarize all of these different things more formally. So the null hypothesis, or H naught, is a starting assumption for a hypothesis test. For the types of hypotheses we'll see today, the null hypothesis always claims a specific value for a population parameter and then foretakes the form of inequality. So H naught population parameter equals some claim value. So H naught proportion of girls born is equal to 0.5. The alternative hypothesis, HA, is a claim that the population parameter has a value that differs from the value claimed in the null hypothesis. It may take one of the following forms: left-tailed, so HA population parameter is less than a claimed value; right-tailed, it's greater than a claimed value; and two-tailed, it's just not equal to a claimed value. So in this case, it would be proportion of girls born is less than 50%, girls born is greater than 50%, proportion of girls born is not equal to 50%. So we can do a couple of examples to make sure that this is clear. Kind of the difference between, what are we looking, how do we set up our different hypotheses? What is an alternative hypothesis? What's a null hypothesis? What's left-tailed, right-tailed? So in each case, identify the population parameter about which a claim is made, state the null and alternative hypothesis for a hypothesis test, and indicate whether the hypothesis test will be left-tailed, right-tailed, or two-tailed. So the first one is the manufacturer of a new model of hybrid car advertises that the mean fuel consumption is equal to 62 miles per gallon on the highway. A consumer group claims that the mean is less than 62 miles per gallon. So pause the video, kind of write out what is the population parameter that we're making a claim about. So what's the population parameter that we're looking at, or that we're trying to uncover with our sample. State the null and alternative hypotheses and whether we're doing a left-tailed, right-tailed, or two-tailed hypothesis test. All right, so the population parameter about which a claim is made is a population mean, or the mean gas mileage of all new hybrid cars of this model, right? So they're making a claim about the mean gas mileage of hybrid cars of a particular model, because they say the manufacturer of a new model of hybrid car advertises, right? So that's what we're talking about. What is for this particular hybrid car, what's the mean gas mileage? The null hypothesis must state that this population mean is equal to some specified value. We therefore recognize the null hypothesis as the advertised claim that the mean mileage for this car is 62 miles per gallon, right? So kind of our starting point is that everything's as it seems. Because someone's making a claim that it's different from what's advertised. So our starting point, our null hypothesis, is that nothing's different. And if nothing's different, then the mean gas mileage of the hybrid cars is 62 miles per gallon. The alternative hypothesis is the consumer group's claim that the true gas mileage is less than advertised. They're saying, a consumer group, that they get less than 62 miles per gallon, right? So that's the alternative hypothesis. That's kind of the one that we'd like to be testing to see, is it true, this consumer group claim, based on, say, a sample that we take, is it true that for all the hybrid cars in that class or of that type, that the mileage or gas mileage is less than 62 miles per gallon? So to summarize, H naught, a null hypothesis. So it's the mean is equal to 62 miles per gallon. The alternative hypothesis is that the mean is less than 62 miles per gallon. And because the alternative hypothesis is in a less than form, we're doing a left-tailed test, hypothesis test. All right, a second example. The Ohio Department of Health claims that the average stay in Ohio hospitals after childbirth is greater than the national mean of 2.0 days. So again, what is the population parameter that we're interested in? What's the null hypothesis? What's the alternative hypothesis? And is it left or right-tailed? So pause, write those out, and then we can return to see if you got the same thing that I did. All right, so the population is all women in Ohio who have recently given birth, and the population parameter is their mean stay after childbirth in Ohio hospitals. So it's limited to Ohio hospitals. The null hypothesis must be inequality. So in this case, the claim that the mean hospital stay equals the national average of 2.0 days, right? Because remember, the group was saying that Ohio is different from 2.0 days. So the null hypothesis is just that it's equal to, the national average. The alternative hypothesis is the health department's claim that the mean stay in Ohio is greater than the national average, right? So greater than in this case. So we've got a null hypothesis of the mean stay is equal to 2.0 days. We've got an alternative hypothesis that is greater than 2.0 days. Because the alternative hypothesis has a greater than form, the hypothesis test will be right-tailed. So once we've done our hypothesis test, what can we get? What are the possible outcomes? Well, there's two possible outcomes to a hypothesis test. First, we can reject the null hypothesis, in which case we have evidence in support of the alternative hypothesis. So if we find that it's really unlikely to get, 64% girls born, if the true population mean is 0.5 or population proportion is 0.5, then we can say that it seems like the null hypothesis is wrong or doesn't fit here. And so we would have evidence in support of the alternative hypothesis. Again, we haven't proven the alternative hypothesis, but we have evidence that supports it. We can, or the second possibility is that we not reject the null hypothesis, in which case we do not have enough evidence to support the alternative hypothesis. So it might be that 64 isn't that unusual. So in that case, we're just not, we're not really sure. Say there's a 50% chance that you can get or a 30% chance that you can get a sample of 100 where there's 64% of them are girls, if just in general. That means that there's a 30% chance that our sample's just we would get that just randomly if the population if even if gender choice did nothing, we'd have a 30% chance of just getting that sample. In which case, if there's a 30% chance of just getting that randomly, then it's hard to say we reject the null it would be hard to say that the null hypothesis is wrong. Now, that's not necessarily saying that with gender choice that is wrong too. There's a fairly high chance, that it's not. That's still a fairly sizable difference. 30% is still quite low. So in this case, we would kind of we can't reject the null hypothesis. We can't say it's wrong, and so we don't have evidence to support the alternative hypothesis, right? But it doesn't necessarily mean that say gender choice didn't do something, but we don't have evidence to support it, and because we don't have evidence to support it, then we can't make any claims that what gender choice says is true. Now, you may notice that there's not a third option called accepting the null hypothesis. So accept the null hypothesis is not a possible outcome because the null hypothesis is always a starting assumption. The hypothesis test may not give us reason to reject this starting assumption, but it cannot by itself give us reason to conclude that the starting assumption is true, right? Because we're not actually testing whether the null hypothesis is true. We're testing the likelihood of getting a sample greater than with a population or with a sample proportion greater than 0.64. We're not actually testing whether the population proportion is actually 0.5. So we can't make actually any claims about whether the null hypothesis is right. So remember, even in the example where I said, that we can't reject the null hypothesis because there's a 30% chance you could still get it. That's still only a 30% chance. So it's hard to say that from that we couldn't say that the null hypothesis is right, because we don't really have any basis to do so. That's not what we've been testing. All we can say is that we can reject the null hypothesis because we have evidence that supports that, say, 64% is just really, really, really unlikely. If the population proportion is 50, so that's one option. And say the population proportion, say 64%, wasn't that unlikely, then we can't reject the null hypothesis. But that doesn't mean, again, that we could support it. We don't know that it's right. We just know that we can't reject it yet. We can't say that it's wrong. So how do we draw conclusions? So far I've talked about if it's far enough, it's unlikely enough. Well, how do we draw these conclusions? What is unlikely enough? What's extreme enough? What's a big enough outlier to get us to say, okay, we can reject that null hypothesis. That sample, that 64% is really, really unlikely, so we can reject the null hypothesis. Well, what does really, really unlikely mean? And we need certain cutoff points. So we decide the outcome of a hypothesis test by comparing the actual sample result. So what you get in your sample, so that 0.64 to the result expected if the null hypothesis is true, so 0.5 say. And we must choose a significance level for the decision. If the chance of a sample result, at least as extreme as the observed result, is less than 1 in 100, or 0.01, then the test is statistically significant at the 0.01 level and offers strong evidence for rejecting the null hypothesis, right? So this one means that, say, you get that 64 girls in a sample of 100. And if we look at, the statistics, and we see that getting that 64% is, getting that 64 girls, that's only going to happen 1 in 100 times if the null hypothesis is right, and the true population proportion is 50% because the gender choice did nothing. And so if that 64 girls is so unlikely that you'd only get that 1 in 100 times, then we would say it's statistically significant at the 0.01 level, meaning that there's only 1 in 100 times would you get that sample mean if the true population proportion, or that sample proportion, if the true population proportion is 0.5. And so that's really strong evidence for rejecting the null hypothesis, right? Because that's only 1 in 100 times, so 99 out of 100 times. You would, if you took a sample of 100 children from, if the true population proportion is 0.50, only one of them would be at 64%, 64% of them being girls. And so that's really unlikely then. That's evidence saying that it's really unlikely that our sample came from a population where the population proportion is 0.50. Right? It seems like maybe gender choice did something, and so for those who take gender choice, the population proportion is greater than 50. If the chance of a sample result, at least as extreme as observed result, is less than 1 in 20, or 0.05, so a 5%, then the test is statistically significant at the 0.05 level and offers moderate evidence for rejecting the null hypothesis. Right, so that would mean if we had a population proportion of 0.5, so our null hypothesis, so 50% boys, 50% girls, that are, say, 64%, we'd get one as extreme, only 5%. So we'd get 64 girls or greater only 5% of the time, so 1 in 20. And so that's still telling us, that's possible that we just got really unlikely and we got that 1 in 20. But normally, but we're willing to live with that risk, right? If we choose the 0.05 level of statistical significance, we're saying, there's a 5% chance that we're wrong, right? There's a 5% chance that we got unlucky, and that it's, we just got that rare one that's that extreme. But we're willing to live with that, one in that 5% chance. And what seems much, much, much more likely is that the gender choice worked, and so we got 64 because the true population parameter is greater than 0.5. So it seems like gender choice did something, right? We can't be certain. That's why we can say that there's evidence in support, but that's partially why you can never say proof, right? Is that there's never going to be, it's impossible to say there's a 0% chance that you got that 64, right? Just by the way that the curves work, those tails never hit 0. So there's never a 0% chance. But at some point, we've got to say, okay, this is unlikely enough. If the population proportion is 0.5, it's just, it's really unlikely that we're going to get 64 if the population proportion is 0.5. And that really likely, it's slightly subjective what we choose, but by convention, we go with 0.5. So, only in 1 in 20 times would we get it. So, 19 times out of 20, you'd be fine. Or that 1 in 100, only 1 time out of 100 would you get it. So it's really unlikely. It's only a 1% chance that you just got unlikely and got that weird sample. And so because it's very unlikely you got that weird sample, that gives us quite, evidence for saying that it's more likely that null hypothesis is wrong, that gender choice did something. And if the chance of a sample result, at least as extreme as the observed result, is greater than the chosen level of significance, 0.05 or 0.01, then we do not reject the null hypothesis. And so that's where I said that fail to reject is a little ambiguous and why we can't accept the null hypothesis. Because, for example, you could have only a 10% chance of getting 0.64 if the population proportion is 0.5, right? Say that's the case. That's still only a 10% chance of getting it. That's still quite unlikely, right? That still means 9 times out of 10, you would not be getting that. So it still could be that gender choice is doing something, but by convention, we say that's too high of a chance of being wrong. So we don't want to reject the null hypothesis above 0.5 usually, because it's too high of a chance of being wrong. We're not confident enough that this is coming from a different population. So that the population proportion when you take gender choice is different. It doesn't necessarily mean that it doesn't do something, but we don't have the evidence to support. But it also doesn't mean that the null hypothesis is right. Right, again, because it could still be very unlikely. It could be, only a 7% chance of getting that sample. That's still really, really unlikely. It could be a 10% chance of getting that sample if the null hypothesis is right. That's still really unlikely. But by convention, we say that to have confidence, or usually we choose either 0.05 or 0.01 levels of significance, and saying we're only tolerating a 1 in 20 or 1 in 100. If we're going to say that we support the alternative hypothesis, if we reject the null hypothesis, we want to be at least 95% certain or 99% certain that we're not making a mistake. So the p-value or probability value for a hypothesis test of a claim about a population parameter is the probability of selecting a sample at least as extreme as the observed sample, assuming that the null hypothesis is true. So a small p-value, such as less than or equal to 0.05, indicates that the sample result is unlikely and therefore provides reason to reject the null hypothesis. A large p-value, such as greater than 0.05, indicates that the sample result could easily occur by chance, so we cannot reject the null hypothesis, right? So every different sample that you take will have a probability value of getting that something at least as extreme. And we've seen, to a certain extent, we've seen these when we are looking last time at the probability of getting a sample at least as extreme. So we've seen probability values, we just didn't call them that last And even here, when we're talking about significance levels, we're talking about probability values. Talking about we're accepting a 0.05 chance or a 0.01 chance of getting something at least as extreme. But when we're talking about choosing significance levels here, we're choosing a cutoff point. These are the cutoff points where we accept or reject the null, where we reject the null hypothesis, or where we fail to reject the null hypothesis. But every different sample we take has a probability value. And so what we choose based on what we saw on the last slide is based on the probability value, whether it's low or high. Is it below our critical or is it above our critical value? So a small p-value, but just in general, even without the critical values, we know the smaller the p-value means that the result is unlikely. A larger p-value means that the sample is not necessarily likely, but it's more likely. So the interpretation of p-values can be summarized by: we reject a null hypothesis if p-value is less than the significance level, such as 0.05. So if we choose that we're willing to take, only a 5% chance of being wrong, so a 5% chance that, it's just we got unlucky with our sample. So what we would need to do for each sample we get is we first need to choose what is our critical. Are we going with the 0.5 level? Are we going with the 0.01 level? So what's, the probability of being wrong that we're willing to tolerate? And then we need to find what the p-value is for our sample. And then we can make the decision, do we reject H naught? And we reject H naught if the p-value is less than or equal to the significance level. So let's give a try. So consider the gender choice example in which the sample n is equal to 100 and the sample proportion is p is equal to 0.64. Using techniques that we'll discuss later in the course, it's possible to calculate the probability of randomly choosing such a sample or a more extreme sample with p is equal to, or some proportion is equal to 0.64 under the assumption that the null hypothesis is equal to 0.5 is true. The result is that the p-value is 0.0026. Based on this result, should you reject or not reject the null hypothesis? Right, so we've got n is equal to 100. We've got the population proportion is 0.64 that we found. So is it possible to calculate the, yeah, because today we're not going to be calculating the p-values. So I'm just going to tell you that if you make the assumption, the null hypothesis assumption, and so then this just becomes one sample. So in one sample of all the possible samples of size 100, you get the proportion is 0.64. There's only a 0.0026 probability value that you'd get a proportion that extreme when the null hypothesis is 0.5. Based on this result, should you reject or not reject the null hypothesis? So think about it for a few seconds and then write down what you think, and then we'll take a look. So the probability of 0.0026 means that if the null hypothesis is true, meaning that the true population proportion is 50%, the probability of drawing a random sample with a sample proportion of at least a p is equal to 0.64 is just slightly under 3 in 1,000, which is pretty low. Because this probability is less than 1 in 100, this result is statistically significant at the 0.01 level, right? Because this is less than 0.01. It therefore gives us good reason to reject the null hypothesis, which means it provides support for the alternative hypothesis that gender choice raises the proportion of girls to more than 50%. So again, using this formulation, and if we're going with, say, the 0.01 level, we reject H naught. So we reject H naught of the proportion is equal to 50% if the p-value is less than our chosen significance level. So either 0.01 or 0.05. In this case, we had a p-value of 0.00026. So 0.00026 is less than 0.01, and so we reject H naught. If the p-value had been greater than 0.01 or 0.05, say it would have been greater than 0.05, so it was a 0.13, then we would fail to reject H naught. All right, so hypothesis testing for population means. So starting to look a little bit at how we actually do this and how does it, we've kind of talked a bit, and hopefully you've been seeing how this relates to what we've done in the last class, but this will make it a little bit more concrete. So considering the following hypothetical situation, Columbia College advertises that the mean starting salary of its graduates is $39,000. An independent organization suspects that this claim is exaggerated and decides to conduct a hypothesis test to seek evidence to support its suspicion. So the null and alternative hypotheses are, so H naught is that the mean starting salary is equal to 39,000, and the alternative hypothesis put out by the independent organization is that the mean starting salary is less than $39,000. And so we're doing a left tail test because it's a less than. So they select a random sample of 100 recent graduates from the college. The mean starting salary of the graduates in the sample turns out to be, so the mean for this sample is equal to $37,000. Testing the hypothesis requires finding the likelihood of observing a sample mean as extreme as the one found under the assumption that the null hypothesis is true. Right, so we take 100 graduates and we get a sample of 37,000. So there's two things that are possible, right? So it could be that the school is wrong in making their claims that the starting salary is $39,000 and it's less, and that's what the organization's doing. It also could just, so we could look at this 37,000 and say that's different from 39,000, and so it seems like that our organization's right. The alternative thing that we could look at is saying that we're just taking a random sample of 100 people, and yes, 37,000 is different from 39,000, but just based on chance, we might have gotten a sample that's relatively low, and so it could just be that it's based on sampling error. We saw last time that every different sample you take, there's some level of sampling error that's different from, so the sample mean will be different from the population mean. So, one time you might get 37,000, one time you might get 41,000, one time you might get 40,000, one time you might get 38,000, right? And that's just based on how sampling works, right? When you're taking a random sample of 100 graduates, you're going to cluster close to, and if you take every single possible one, the mean of all samples would be the population mean, but there's going to be some difference between all of your different samples. So what we're trying to figure out is it the case that getting this 37,000, is that evidence that the claim of the school is wrong, or the claim that the organization making is right? So is it that the true population mean is less than 39,000, or is it just the case that this is just bad statistical luck in our sampling? So for the Columbia College example, the question becomes this: how likely are we to select a sample of size n equals 100 with a mean of 37,000 or less when the mean for the whole population is 39,000? And this is now looking, a lot like what we did in the last class and questions we had on the last quiz. So to answer this question, we need crucial information. So first we have to realize that our sample, right, is coming from a wider, distribution of sample means. So it would be very possible to take that this is just one example or just one sample of the many, many different ones that would make up the distribution of sample means. And if then we remember that, this is just one sample of a distribution of sample means, and that distribution of sample means have certain properties, then we can start figuring out how unlikely is this. So assuming the null hypothesis is true, this distribution of sample means is approximately normal with a mean of 39,000. So if we assume the null hypothesis is true, right? Because we're going to test it, it's we operate always under the assumption to start that the null hypothesis is true, and then we look at how unlikely is it to get if the null hypothesis is true, how unlikely is it to get 37,000. So if the null hypothesis is right, then we're looking at this is one sample in a sampling distribution that is approximately normal, and where the mean is the population mean. The mean of the distribution, or the sampling distribution, or the distribution sample means, is the population mean of 39,000. So this would be the case if the null hypothesis is right. So we can then look, based on the assumption that the null hypothesis is right, and based on what we know that we're dealing with a normal distribution with a mean of 39,000, and we're dealing with a normal distribution, we can start to figure out how unlikely is this 37,000. So here's looking at one-tailed hypothesis testing. So an example with one-tailed hypothesis testing. So if the null hypothesis is true, the population mean is 39,000, right? So this is the sampling distribution, right? So these are all the different samples, all the different samples are means. If we took many samples from the population, the distribution sample means would be approximately normal. So that's how it got to be a normal curve with a mean of $39,000. Under this assumption, the distance of a single sample mean from the population mean allows us to decide whether to reject or not reject the null hypothesis, right? Because we saw last time when we're dealing at least with standard normal distributions, that for anything under the curve, for any value along here, we can find what's the probability of getting something at least as extreme. So say this, or of getting this value and higher. So here's our mean. The red curve is a sampling distribution. Here's a sample mean near the peak. It's fairly likely. So gives us gives us no reason to reject the null hypothesis, right? It's quite likely if you just take a sample that look at how likely this is, look at how much of the probability is still under here. This seems, if we get a sample and it say this is 38,000 or 38,500 or whatever it would be, this is really close to the mean, high probability that we just get this sample just randomly. So we would have no reason we can't say that the true population mean is 39,000, but we have no reason to say it's wrong. We can't say it's right, but we have no reason to say it's wrong. Say though we get a sample out here, right? A sample mean far from the peak. It's unlikely, so it's suggesting the null hypothesis is wrong, right? Because so if we get a sample mean out here, it's not necessary, like it's not 100% certain that the null hypothesis is wrong, but it's very, very unlikely to get a sample mean this extreme, right? So it's possible that you just got, again, unlucky, but what seems more likely is that this is not the true sample, the true population mean. Maybe the population mean's over here, and then getting that sample would be much more likely. Because the sampling distribution is a nearly normal distribution, the standard score of the sample mean represents a quantitative measure of the distance between the sample mean and the claimed population mean. Recall that the standard score, or Z-score, of a data value in a normal distribution is a number of standard deviations that it lies above or below the mean of the distribution. So this is just kind of figuring out, okay, so how unlikely is this or this based on the standard score? Because we saw last time that if you're dealing with a standard normal, for any point along here, we can find out the probability of getting something at least as extreme, or based on the standard score table, we can find the probability of getting something less than that. So in a later class, we'll discuss a better way to proceed when the population standard deviation is not known, because in reality it won't be. But in this case, I'm just going to tell you that consistent with what we've done last time, that the population standard deviation is 6,150. And so what we saw last time is that if you know the population standard deviation and if you know the sample size, you can find the standard deviation for the sampling distribution. So for this. And that we found the standard deviation for the sampling distribution, that's simply the population standard deviation divided by the root of the sample size. So 6,150 divided by, oops, that should be root 100. Yeah, so that actually should be, yeah, there's a mistake here. It should be root 100, so 10, but the number is still right. So it's still 615 because 6,150 divided by 10 would be 615, but this should be root 100 or 10. Using the value in the previous equation tells us that the standard score for the sample mean of X bar is equal, so sample mean is equal to $37,000, and the sampling distribution with the population mean of $39,000 is, so the Z score, we take our sample mean, our population mean, divided by the standard deviation, so the mean of the sampling distribution, divided by the standard deviation of the sampling distribution, and that gives us a standard score of negative 3.25. So it's 3.25 standard deviations below the mean of the sampling distribution, which is pretty far. If you just before even looking at any tables, or 3 standard deviations away, it's pretty far. So recall that the hypothesis test is significant at the 0.05 level if the probability of finding a result as extreme as the one actually observed is 0.05 or less, assuming the null hypothesis is true. For a left-tailed test, then, we're looking for a standard score that is at or below the 5th percentile of the sampling distribution. Because the 5th percentile means that there's a 5% chance of getting that value or a lower value of the sampling distribution. From the standard score table, the 5th percentile has a standard score of minus 1.645. So therefore, a left-tailed hypothesis test is significant at the 0.05 level. The standard score of the sample mean is less than or equal to minus 1.645. This standard score represents the critical value for significance at 0.05 level in a left-tailed hypothesis test. So just going back quickly, right? So if you find, so assume we've standardized this, right? So you've got a mean of 0 and a standard deviation of 1 because we've standardized it, right? If you get out to negative 1.645, then anything more extreme has a lower percentage or lower probability than 0.05 or lower percentage than 5%, right? So there's less than a 5% chance of, say this is minus 1.645 standard deviations below. So there's less than a 5% chance of getting that or anything lower than it. So that critical value is important to remember. There's a few critical values that are important to remember because it tells you that if you find your standard score and it's bigger than that, then you can't reject the null hypothesis, or you fail to reject the null hypothesis. If it's more extreme than it, then you can reject the null hypothesis. So in our case, right, minus 3.25 is more extreme than minus 1.645. So there's less than a 5% chance that we would get that sample mean, or we get that sample mean if the null hypothesis is true. So actually it seems in that particular case, the example that we had, that getting 37,000, a sample of 37,000 is actually very, very unlikely if what the school was saying is true. So we have support for the alternative hypothesis that the starting salary is less than 39,000, because it's very unlikely if we took 100 students and that were true, it's very unlikely, at less than 5% chance that we would get that sample if it were true. So one-tailed hypothesis tests. So we looked at one case where it's left-tailed. So sample mean with the standard score less than or equal to the critical value of minus 1.645 is significant at the 0.5 level if you're doing a left-tailed test. If you're doing a right-tailed test, a sample mean with the standard score greater than or equal to 1.645 is significant at the 0.5 level, right? Because this part, anything under this curve here means, or the entire green area over to here adds up to 5% of this entire curve. The green over here up to that 1.645, all of this is equal to 5% of this entire curve. So what we're looking at, so say you get something out here, beyond that, we know that there's a less than 5% chance of getting it. Same thing over here. If you get something over here in this green, you know there's a less than a 5% chance getting it if the null hypothesis is true. So yeah, left-tailed test. The hypothesis is less than a claimed value. For the 0.05 level, we reject the null hypothesis. The standard score is less than minus 1.645. For right-tailed, we do it if it's greater than 1.645. And for the 0.01 level, reject if it's less than 2.33 or negative 2.33 or greater than 2.33. We use the 0.05 much more frequently. So these are the good ones that kind of commit a little bit to memory. That it's still easy to find, even if you don't remember it. You can find it in a standard score table, so it's not a problem. So recall that the p-value is a probability of finding a sample mean as extreme as the one found under the assumption that the null hypothesis is true. So getting a sample mean of 37,000 given the null hypothesis of 39,000 is true. For a left-tailed test, the probability of finding a sample mean less than or equal to some particular value is simply the area under the curve to the left of the sample mean, right? So this for the left-tailed. For the right-tailed, it would be in this area. So just kind of zoomed in a little bit here. So that's where kind of the critical values come in. But even without it, right? Even if you just put, okay, so I found one here. I could take the standard score and find my actual p-value. So what is the exact probability? For two-tailed tests, a value as extreme as the one actually found can lie either on the left or on the right side of the sampling distribution, because we're saying it's just not equals, but we're not committing to which side. We're just saying it's not equal to, say, 39,000, but not that it's less than or greater than, say. A probability of 0.05 or 5% therefore corresponds to a standard score either in the first 2.5% of the sampling distribution on the left side or in the last 2.5%, right? Because if we're saying 5%, but we're not sure which side, we have to split that 5% to half of it being on the right side, half of it being on the left side. So we put, if we're to say that, if we're to reject the null hypothesis based on a two-tailed test, it's got to be either in the smallest 2.5% of the sampling distribution or on the largest 2.5% of the sampling distribution. From the standard score table, the 2.5th percentile corresponds to a standard score of negative 1.96, and the 97.5th percentile corresponds to a standard score of 1.96. So 97.5, because that means that 97.5% would be smaller than it, which means 2.5% would be larger than it. Because remember, percentiles or the standard score table, it's always saying less than. So if you want to be doing greater than, you've got to do 1 minus. So these standard scores become the critical values for two-tailed tests to be significant at the 0.05 level. So these are also important to remember. Remember, they're also very close to 2%. And we saw these, the 1.96 last time. Yeah, so here, two-tailed test. So your critical value, so if you find your sample mean out here or out here, then you can reject the null hypothesis. If it's anywhere in here, then we can't be 95% sure that it's not just due to an unlucky sample. Where if it's out here, then there's one of these, then we can say there's only, at most a 1 in 20 chance that you would get this sample if the null hypothesis were true. So statistical significance, a two-tailed test is significant at the 0.5 level if the standard score of the sample mean is at or below the critical values of negative 1.96 or above the critical value of 1.96. So that's kind of just summarizing what we just said. For the 0.01 level, the critical values are minus 2.575 and 2.575. You don't have to remember those as much. Finding p-values is a little tougher for two-tailed tests because you've got one side and the other side, and the table's only showing you, less than. So to find the p-values for sample mean in a two-tailed test, first use the standard score of a sample mean to find the p-value, assuming the test is one-tailed, then double this value to find the p-value for the two-tailed test, right? Because remember, once you found it for less than, we also need for greater than, so you need to double it. All right, so that's it for hypothesis testing. I know that a lot of what we just saw is going to be confusing kind of on the first time, but we're going to be continuing with hypothesis testing. So remember, this is building on what we did last time. So a lot of kind of how this works is just based on normal distributions and standard score tables that we saw last time, and on sampling distribution. So we're just looking essentially, assume the normal the hypothesis is right. So we know what the mean of the sampling distribution is, and then we want to see how unlikely is it to get that sample. That's all we're doing. So the procedure is almost identical to what we did last time. The critical values and stuff like that is a little different. And next time we're going to be building on it. So we're going to be seeing more examples like this, and we're going to start relaxing and making some of the assumptions more realistic. So in particular, we're going to start looking at what happens if you don't know the population standard deviation.